Thanks very much, and thanks for the invitation. It's a great pleasure to be here. So let me sort of start by setting the context for the kinds of problems we want to talk about. So I'm going to be working with a map between two different spaces. Let's call them omega and x, such that both omega and x have complex algebraic structures. So what that tends to mean in practice is that they're either algebraic varieties over C themselves, or they're open subsets inside algebraic varieties, one of those two things. And the map pi is holomorphic, but typically not algebraic. And then the question that I want to talk about is, to what extent do the algebraic structures between omega and x interact? So let me start just by giving sort of the examples just have in mind, and these are basically what I'm going to talk about. So the first and sort of classical case that was thought a lot about in the 70s is the case of exponentiation. So we can look at the exponential map, which I'll call exp, from C to the n to C star to the n. And all we're going to do is we're going to send an n tuple of complex numbers to their exponentials. And because we're number theorists, it's sort of convenient to put the 2 pi I in there, even though it doesn't really matter for anything I do. You can re-say everything without the 2 pi I. It just sort of makes things a bit cleaner. So that's sort of a basic case where you have a transcendental map between them. It's not hard to show that E is not algebraic. And these both have algebraic structures. And if you sort of look here, you're thinking about regular polynomials and sort of polynomial relations. And if you're looking in this world, you're sort of looking at trig polynomials, like polynomials in sine, cosine, and e to the z and stuff like that. And the second example I want to talk about is sort of the simplest Shimura example, where, so now we don't have an algebraic variety over here, and this is sort of typical in the Shimura world. But the upper half plane is sort of a natural subset of the complex numbers, or more naturally the projective line. And so you certainly have an algebraic structure over here, and you can sort of talk about algebraic varieties intersecting the set. And you certainly have an algebraic structure over here, and you can ask to what extent they interact. And then more generally, you can just sort of take omega to be a symmetric space of an appropriate type, and x to be a Shimura variety. Okay, this is ultimately the case that I'm going to talk about today. Okay, so what do we mean by to what extent do these algebraic structures interact, sort of how to make that precise? So there's a few sort of levels. Well, there's many different questions you can ask, but there's three, I think, sort of natural gradations of information you could ask for. So the first information you could ask for is, what are the bialgebraic sets? In other words, what algebraic relations can be written either in this world or in this world? Or said more formally, we want V in omega and W in X, such that V and W are actual algebraic varieties in the respective algebraic structures, such that pi of V is equal to W. Where a pi of v is the risky closure is W. I mean, up to sort of minor issues like that, this is basically what we're interested in. So that's the first kind of thing you can ask for. And the answers end up being sort of things that we consider interesting structures in general. So in case 1, what are the algebraic sets? Well, the exponential function satisfies a very simple algebraic relation, which is if you add in the first world, that's the same thing as multiplying in the second world. So in other words, the graph of addition over here just translates to the graph of multiplication over here, and that's a algebraic set. And in general, the algebraic sets are V is an affine linear subspace with rational slope. So V is a translative of a linear subspace that can be defined by imposing rational linear additive relations. You can't sort of remove the rational slope here, because if you take like z1 equals I times z2, you get nothing algebraic on the other world. You can't take things to the power of I. Or in other words, equivalently, W is a coset of an algebraic subgroup. This provides sort of a nice characterization in terms of transcendence theory and algebraic structures of these sort of natural subvarieties we might care about in the first place. OK, and in world 2, so for example, with the J case over here, you don't have rational relations, but you can still say certain things in both worlds. For example, in C to the n, which you can think of as the moduli space of elliptic curves to the n, you can insist 2 elliptic curves are isogynous by a cyclic isogeny of some degree. And over here, that will translate to some linear or very simple relation. And so in general, for V and W to be bialgebraic like this, W must be defined by setting 2 coordinates to be isogynous or 1 coordinate to be constant. Okay, and that's basically the only way it turns out you can get things algebraic in both worlds, is just pick a bunch of coordinates, insist in a bunch of isogenies, and pick some other coordinates and make them constant. There's nothing else you can do. And more generally, in the third case, in order for this to happen, you need W to be essentially a Shimura subvariety. I say essentially because you're allowed to sort of translate a little bit. For example, in this case, if we have x1 squared and we take the first coordinate to be a non-CM elliptic curve, then that's bialgebraic, but it's not really a Shimura variety. And so there's a notion of sort of a translate of a Shimura variety, which makes this work, which I don't want to define precisely, but it's sort of a very clean description of these things. So the first two, well, the first one's classical. I guess the second one is due to Jonathan Pilla, I think. These might be much older. And the third one is due to Klingler, Ulmo, and Yafev.
What happens in example 1 if I took an exponential for some other algebraic group?
Instead of C to the n, like a commutative group?
No.
Or a non-commutative group? Good question. So I think if you take like SO2 or something, it becomes hard to define. Oh, I see what you're saying. You're saying the Lie algebra of SO2 and exponentiate.
Yeah.
Ah, that's a good question. I haven't thought about it at all. Yep. Okay. So that's sort of the first thing you can ask for, and we basically know this in all cases of interest. Okay, then you can insist on other things. For example, you can ask which algebraic relations over here can I impose by doing something over here? Right? So when can I if I take an algebraic variety here, maybe I can't cut it out exactly with relations here, but maybe I can still cut out something which includes it using relations here. So formally speaking, I can ask when is pi of v for the same setup contained in W. So in the classical C to the n case, I'm asking when can I impose some algebraic relations or take an algebraic variety here which satisfies some non-trivial trigonometric polynomials. This is already a much more complicated question. And the answer becomes, so I'll write this as, because of the general setup, these results of a certain type have acquired a uniform nomenclature. So this type of result has been dubbed by Jonathan Pilla to be an Ax-Lindemann type result. So I'm going to state it at once for all of these cases. And it's called this way because Ax sort of did all of everything in this setting of exponentiation. And the Lindemann is there because of some number theoretic inspiration that I don't want to go into. But in any case, this is the nomenclature. And the theorem says the following. Well, what's an easy way to set this up? So one thing I could do is I could take a variety which is algebraic in both worlds, take V to be something inside it, and take W to be something containing it. And that'll certainly give me an example of this. And that's sort of cheating, because I've started something by algebraic, and I've just sort of done trivial operations from there. And the Ax-Lindemann theorem, maybe I should make it a claim, but it's a theorem in all of these settings, says this is the only thing you can do. Says that if this is the case, there exists a bi-algebraic S. I could make S either in omega or in X. I'm going to choose to state it with S and omega, with V in S and pi of S in W. So in some sense, the only non-trivial interactions are the ones that show up from bi-algebraic sets.
What does question V of W depend on the image?
So V is an algebraic subvariety on omega, and W is an algebraic subvariety of X, the entire time. That's sort of the basic setup. That's how we're recording the interplay between these two. Other questions? OK. So then you can ask for even more information. So you could say, well, OK, maybe I can't get algebraic relations in one world to imply the other without doing something trivial. But maybe if I include relations from both, I can sort of impose fewer conditions than I intended to. So maybe a concrete way to see this is if I take, say, a three-dimensional variety, so take n equals 3 here, and maybe I can impose, well, that's a bad example. No, let's take n equals 4, and maybe I take an algebraic surface here and an algebraic surface here. So that's sort of two conditions in this world and two conditions in this world. And maybe if I impose them both, I get a curve. And that's sort of surprising, because you expect them not to interact, and so you would expect 4 conditions to just cut out a point. And so a good way to record this notion of dimension, there's sort of a nice model theoretic way to talk about dimension. But since we're in the holomorphic world anyways, holomorphic dimension suffices for our purposes. And so we can ask, so we call, so let me say it this way. So take U to be an analytically irreducible component of V intersect pi inverse W. And we say that U is unlikely
The thing about
yes.
definition, and it's a theorem that Ax-Lindemann is true, in all these three cases? Or
So it's a theorem which Ax has proved in this case,
the other?
and in the other cases, so Pilla has proved it in this case, and in the general case here, Klingler, Umo, and Yaffaev have proved it. Yeah, so Ax has only thought about this case and some semi-abelian cases. He's done work there as well, but he hasn't thought about the Shimura context at all. Sorry if I'm making the attribution confusing. So we say U is unlikely if precisely this kind of surface-surface curve example shows up. So basically, if the codimension of U is less than the codimension of V plus the codimension of W. And so then, well, let me make this a claim to avoid doing the same kind of mistake I did over here. And let me call this claim Ax-Schanuel for any particular setup. And the claim is, again, the only way you can have something like this showing up is if you have some bialgebraic stuff that's responsible for it secretly. So there's many different ways to say it. The cleanest one, I think, is that if U is unlikely, then U is contained in a proper bialgebraic set. And
It's a definition.
I'm sorry?
You said a claim. It's a definition.
No. The definition is here. So
That's the definition of unlikely.
yeah, and this is a claim about unlikely sets. I'm confused. Sorry.
Classification. Okay. I mean, you're saying that the only way unlikely can happen.
Is right in this way.
All right.
Okay.
Theorem.
It's a theorem in many cases,
Yeah.
right? So I'm going to say when it's a theorem in a minute. Yeah. But I just want to set it up as a general claim in every context, even the ones where it's not a theorem. Yeah, that's something which you might want to strive to prove. All right, so the simplest way to sort of see why bialgebraic sets can get in the way, just like in question 2, is in some sense, if U is contained in the proper bialgebraic set, you're taking the codimension in the wrong space. Right? I mean, for example, here we could secretly be working in C to the 10, but have set up the question in C to the 30. So the 30 there isn't really doing anything if you're really inside a proper bialgebraic set, which is why you have to watch out for that case. OK, so let me now say when it's a theorem. So in the case of the exponential function, this is a theorem of X. Sorry, X. Theorem of X in the 1970s. And he actually didn't set things up in this 1, 2, and 3 way.
I just want to clarify what's
I'm sorry.
that's a property of your setup, which you're now going to tell us when it's true.
Yes, that's right.
Better way to say it.
OK.
You say you have the Ax-Schanuel property, if that holds.
Yes, that's right. Sorry, I've bungled things up. This is a claim, and claims can be false. Is the way I'm setting it up, which maybe it's a property. It's a property. 15 minutes in, and I've confused everybody. All right. So
Sorry,
yes.
the definition of unlikely depends on V and W.
The way I've said it, yeah, but you could just think U is unlikely if there is a V and W where this is true. That's sort of a fine way to say it.
This is independent.
Yeah, that's right. So you can say that U is unlikely if there exists V and W where U is a component, and this is true. And then that's a property for unlikely intersections. OK, so in the exponential case, it's a theorem of X. And he sort of phrased everything in question 3 at once. And he didn't even use the geometric setup. He basically used the differential equation of e to the x to phrase everything in the language of differential fields. And he just sort of did a lot of very clever algebra that I haven't understood. And he proved this theorem. Excuse me.
And presumably he proved the analog of the Schanuel conjecture, which is why Schanuel is named.
That's right. That's right. So this whole thing is inspired by Schanuel's number theoretic conjecture. So in the J case, it's a theorem of myself and Pilla, sort of pushing techniques that had been used to study the Ax-Lindemann criteria in general, but which got stuck in the general Shimura case. And then in the general Shimura case, I want to explain how mock Pilla Tsimerman, right? How a new idea of mock sort of allows us to go further and settle this question in this context. So, yeah, so let me say a couple words about that. So why should you be interested in this if you don't care about transcendence in general? So let me say a few words about arithmetic applications. Yeah, so in some sense, I mean, I started thinking about this, and many people did, because it just sort of came up in trying to prove a lot of arithmetic questions. And it sort of keeps coming up in a variety of unexpected situations. But so one way to think about this, I think, is in the style of the Bombieri-Lang philosophy, or what I'm going to call that, which is basically that if you have some arithmetic thing that happens over and over again, there must be an underlying geometric reason for it. So in the same sense, you can say that a point P in omega is bialgebraic if P is a q-bar point of omega. Now, I haven't really equipped these things with q-bar structures, but in all three of these cases, there's fairly natural ways to do that. And also, its image is a q-bar point of x. So, for example, in the exponentiation case, if you take e to the 2 pi I of rational numbers, you get roots of unity. So if you're studying roots of unity, you can think of them as those points which are algebraic, whose logarithm is also algebraic. And that gives sort of a natural way to think of these guys. And then in the Shimura case, let me skip over the J case right away. I'm also skipping over the abelian variety case, by the way, for which there's a very natural similar picture. And there's semi-abelian things and more general guys as well. In the Shimura case, well, let me do the J case as well. Maybe it was a mistake. So in the J case, if you take J of quadratic irrationals, you get sort of singular values, singular or CM values. So J invariants of elliptic curves with complex multiplication. And in the general Shimura case, you get sort of CM points. Somehow the bialgebraic analogy, you can think of as having this arithmetic counterpart, where instead of looking for curves which are algebraic in both worlds, and that somehow you can think of that as working over function fields, if you like thinking about it algebraically, you can also think just over q bar, and you get sort of similar statements. So that following this philosophy that something arithmetic happens over and over, if and only if there's an interesting geometric reason behind it, you can sort of think of these conjectures about studying when something is algebraic or both worlds, or the extent to which it is. They all have arithmetic analogs. You can think about sort of transcendence degree in both worlds of a point, and you can ask when things are contained in algebraic varieties and things like that. And so in order to get a good grasp on this picture, it sort of becomes a prerequisite to understand the geometric picture, even to sort of have the right statements.
Do we know CM points are only by algebraic?
It's a good question. I believe we do. We definitely don't know the complete analogs of these things. Yeah. And in the J world, I don't even think we know that, like, if you take two q-bar points which aren't CM, their images are like algebraically independent. I'm not an expert. I think we don't know that. We don't know a lot, certainly. But I think this particular one we do know. Though it is hard. I mean, I'm just writing these things down like, oh, it's obvious. But these are all very hard theorems. All right, that's all I was going to say about the arithmetic case right now. OK, so let me say a little something about. I'm going to be ambitious and run out of time. But I want to describe a little bit about the sort of general strategy developed by Pilla as to how these transcendence theorems are proved, explain where it sort of runs into difficulties in the Shimura case, and then I want to say something about this idea of mock, which allows us to go forward. OK. Sorry, this is Ngeiming mock. Ngeiming mock? Ngeiming, OK. Yeah. All right, so the sort of, let's talk about first the classical omnimality argument. To proving these kinds of statements. Let me talk about the idea and a couple of inputs that go into the proof, and I'll explain where those inputs sort of go wrong. So the way I think of the main idea is you start with one supposed counterexample to this. So one pair V and W that have unlikely intersection. And from there, you make many more, which is sort of a similar idea to how actually Andre Yortis proved, where you start by having a CM point and use the Galois action to get many more. And sort of it's hard to work with one, but once you have many, you can sort of say you have much more options at your disposal. So the first idea is, yeah, so that, well, let me first say, so number one. So in all of these settings that I've described, we have pi has a monodromy group. And in fact, the monodromy group is of a very special structure. You can think of it as the integer points of some algebraic group, where G is an algebraic group. And moreover, the complex points of this algebraic group act on omega. This is a white lie. They don't really act on omega. You got to get a little bit bigger before they act. SL2RX never have plane. SL2C only acts on P1, but let's not quibble for right now. And so you have this giant action, which is transitive, and in fact more than that. And inside there, you have the integer points under which pi is invariant. So in other words, what this implies is that if VW gives an unlikely intersection, so I'll just say is bad, instead of saying more precise things, then so is gamma VW, where gamma is an element of the monodromy group. So that's sort of the basic idea. Of course, nothing happened yet. This observation alone doesn't imply very much. The second idea is that the holomorphic world ends up being a little bit too chaotic for our needs. General holomorphic functions, they're sort of better than general real analytic functions, but they're still very messy. And so the second idea is sort of go to a more tame setting. And this is accomplished by the theory of omnimality, and I don't want to say very much about that. So I'll just say the following. You can take F to be a nice fundamental domain. So in the case of the exponential map, you just take a horizontal strip, the way we've set it up, to the power of n. In the case of Shimura varieties, you take something built out of Siegel sets. And we're going to call this a nice fundamental domain. It's fairly robust, actually, so the exact form of f isn't important. And then if you look at the projection map pi from omega to x, and you restrict it to f, then this is definable in this O minimal structure, Rn exp. So again, I don't want to focus on what this means. Roughly, it means you can build this map out of the real exponential function and subanalytic functions. And it's sort of this sort of is a very nice theory where you don't really have to know what it means. It's very easy to sort of use as a black box. So it just sort of means that reasonable things you built out of pi behave reasonably. So for example, everything we're going to make has finitely many connected components is a big one. We sort of get all sorts of uniformity results for free. It's just sort of a very nice context in which to work.
Can you say what it means for the J function?
For the J function? Sure. I can say roughly what it means for the J function. So for the J function, if you look at J of z, you can write it as R of e to the 2 pi I z, where R is some power series. So let's write it as R of e to the x, no, how does it go? E to the minus 2 pi y, I can do it. Maybe like a times cosine x plus I sine x. That's surely close enough. Let's go with that. OK. So we can write it in this form. So why is this in Rn x? But let me just say that quickly. So first of all, the exponential function is fine. The real exponential function is OK. Cosine and sine are definitely not fine. Because in particular, if you look at their graphs, they cross the x-axis infinitely many times. And that's just not allowed. Z is somehow the worst set in this game. So you want to avoid that. But we don't have cosine and sine. We only have cosine and sine on a bounded interval. And because of that, they're subanalytic functions, because they're real analytic functions that converge on a bigger domain than that which they are defined on. Moreover,
It's a generalization of real and analytic and subanalytic. It's elements, right? But to include exponential.
so moreover, this R is a power series which converges on the ball of radius 1. And it's not enough to just say that power series are good, because they aren't. We definitely want to avoid all analytic functions. But if you look at the, let me continue over here because I have space.
Who invented this notion? Van der Waals?
Of omnimality? It's a good question. Yeah, I think it was Van der Waals. I'm not sure if Khovansky wrote down something essentially equivalent, because it started from his work on exponential polynomials and phenomials. But then Van der Waals probably codified it, yeah. And so if you look at this fundamental domain that we're restricting ourselves to, which is just this in J case, if you pass to the unit disk, it becomes something like this. I don't know. It's probably wrong, but something roughly like this. No? No good? Should hit the boundary. Of course it should hit the boundary. That was a test. Yeah, right. It hits the boundary. So let's make it something like this. That's pretty good? All right, good. Anyways, the point. Ooh, it hits the boundary, does it? That's not good. One second. So, right, so at, yeah, that's right. So at infinity, q is equal to 0. So it's a power series which converges. So this is, I guess this is 0. So it's a power series which converges on radius 1, and you're taking something which is smaller. And so it's subanalytic on this set, even though the whole graph wouldn't be. And so that's why J is good. We've composed 3 subanalytic functions, and so we're fine. The general picture for Shimura varieties, though, it's a bit of a lie to say it's as simple as this. It gets substantially more complicated. And actually, I'll say more about that in my lecture on Tuesday about hard structures and definability. But let me Yeah, so let me leave this for now. All right, where was I? Right, we were in step 2, so this thing was definable. Then the third step is to sort of put this idea to work, that if we have one counterexample, we have many, by sort of looking at the set of possible counterexamples. So we'll let I be the set of elements, complex elements of the group, essentially such that W and GV make a counterexample to this question. But we're going to be a little more careful. We're going to say such that the dimension of GV intersect pi inverse W intersect this fundamental domain is equal to dimension U. So in other words, so the sort of first order way to think about this is we just want other algebraic varieties V which intersect W in too big of a set. And the reason this F is here, which sort of makes the picture more annoying, is because we want something tame, something definable. If we didn't put the F there, this wouldn't be definable because pi inverse W is too complicated of a set. It's a periodic set, and that's bad. So we include this fundamental domain to make things good. If this point is sort of, if I've explained it poorly, then it's not so important for the rest of the talk. But it sort of becomes important in the weeds of things. OK, so then the sort of punchline of all this is the following. Well, this is our set I. So first of all, by what I just said, I is definable in Rnx, so it's a pretty tame set. It's pretty easy to see that I is holomorphic, or roughly holomorphic, up to the fact that it's not necessarily closed, because, well, these are holomorphic actions and holomorphic conditions. The second observation is that I contains much of GZ. So it contains many of the integer points. It would contain all the integer points if we didn't have this annoying F to deal with, but we do, and so there has to be argumentation there. Nonetheless, you can sort of say I contains much of GZ. And so then the conclusion by theorem of Pilla and Wilkie, which is very important, but which I won't even write down, since I is definable, contains many integer points, I's got to have something algebraic going on. I contains algebraic curves. So to summarize, you can summarize the argument very quickly by saying we're looking at the set of possible bad sort of counterexamples to our theorem.
You really wanted to say in V, you didn't.
I think the definition is correct.
You were assuming that only that somehow pi minus W and V have intersection which has too high dimension, no? You really.
Sorry, say that again, please. So we're starting with the assumption that pi inverse W and V intersect in this set U, which dimension is too high.
Yeah.
And then I'm looking at all possible G's such that it's still
The
true.
question is front question. This is a U or a V?
This is a V.
No. Here it's a V, but is that?
This is a U.
Okay, then I understand.
OK. That wasn't a U? OK. All right. Yeah, that's a U. Yes, the idea is we're looking at all counterexamples V and W, the set of all of these. This monodromy trick tells us if we have one, then we have many. And then we have some general structure theorems to tell us, well, if we have many, you've got to have something algebraic going on. OK, so then once I contains algebraic curves.
So this is just the straightforward Pilla-Wilkie theorem applied to.
This is a straightforward Pilla-Wilkie theorem.
Points in GZ with this property, and if there are no curves, then you've got an upper bound.
That's right. That's right. This is sort of another way to state the theorem. If you have many points, then you have curves. That if I am hiding something under the rug, is that the statement is not as easy as it seems to prove. So there's like hyperbolic geometry that goes into here, and there's some other stuff. But that's sort of by now a fairly standard part of the argument.
No, containing an open curve means containing an open path.
Yeah, I mean, I should really put semi here. Contains a semi-algebraic curve, yeah, and then everything's fine. Other questions? Cool. So then we have sort of two cases in the argument.
There's at least one.
Sorry? Oh.
Contains a non-empty. I mean, there's something there.
There's, yeah. Sorry, I'm not doing the best job at being super precise, but that's partly because I don't want to get too technical. So everything I'm saying is morally true, even if some of it's not actually true. So the first, so the idea now is we're going to replace V by the bigger algebraic set. Let me call this curve C that I contains. C times V. That's sort of the push. It's to now do induction because we have all these algebraic guys, in fact, an algebraic family of them, which give you counterexamples. Let's just put them together, get a bigger counterexample, set up some induction, and we're done. OK, and this case is fine. And case 2 is that V is just equal to CV. In other words, V has a stabilizer equal to C times V. And case 2 is sort of the hard part. So this is a simplification which exists in Ax's proof as well, even though it's differential and very different setup. Somehow, if you're in the exponential case, then the group you're dealing with is z to the n. There are no complicated subgroups. Everything's sort of normal and abelian, and everything looks the same. In the general case, in the case of a Shimura variety, you have semi-simple non-abelian groups, and you could have very complicated groups of stabilizers. And this is where the argument got stuck for us. In SL2, Pilla and I managed to push the argument through, because SL2 doesn't have that many subgroups. There are sort of tori and unipotent groups, and that's basically it. There's no semi-simple subgroups of SL2. So actually, our proof for SL2 was this sort of mess where in the unipotent group case, we sort of went back and used classical Ax-Schanuel because that sort of becomes, it sort of looks like that. In the tori case, we used some growth properties, and it sort of was a very ad hoc by the numbers sort of proof, which for higher groups we just couldn't make work. So this is sort of where the classical arguments get stuck. I'm sorry? Oh, we did it to the end. Yeah, so even there you can manage. I think already SL3 we couldn't do. SL3 is not Shimura, but anything containing SL3. All right, so let me now say what sort of new idea Mog brought to the game, which was so good. We first thought we could throw this entire picture out and just work with his idea. Unfortunately, life didn't work out that way. But the reason that, I'll just say that the reason Mog started thinking about this picture is because he he cared about these transcendent results for different sort of reasons that I don't understand still. But his perspective was very differential geometric. And so as a consequence, even in the Ax-Lindemann case, where we're looking at varieties containing each other from the different worlds, he could handle the non-arithmetic cases that we couldn't. So in particular, if you take x to be a hyperbolic curve, which is non-Shimura, then you can still look at its uniformization, and you can take n different copies of it. And this is a very similar setup, so we can ask all the same questions. And there's fewer bialgebraic sets, but we can still write them all down, and there's nothing surprising sort of happening. And in this setting, so Mach could prove, Geiming Mach could prove that Ax-Lindemann is true. And we couldn't, because the arithmetic group, even though it's still discrete, you can't talk about integer points. And our counting theorems don't work. And I thought the fact I thought about it doesn't mean you can't do it. But I thought for a long time about how to move things to that setting, and I can't figure it out. So it seems like there's actually something to do there. Anyways, but he could prove this using what I'm about to describe. And the Ax-Schanuel case, even though we now have it in the Shimura setting, we still can't do over here. Because again, our methods just don't help over here almost at all. So that's still sort of an open question. So Ax-Schanuel, still open.
So what do you mean by algebraic in that sense?
I'm sorry?
Could you say what you mean by algebraic in that text to the end?
Oh, by bialgebraic? Just again, something algebraic over here, whose image here is also algebraic.
What exactly is maybe is algebraic in x to the n? X being some.
Well, x is a hyperbolic curve. So it's just like an algebraic curve of genus bigger than 1. And so x to the n is just a projective variety. Nothing sort of subtle. Yeah, and there might be issues like the image might not be actually algebraic because it might miss some open set or might miss a point, and we're not worried about things like that. Yeah, OK. OK, so Mach's idea was that even though this map is transcendental, you can actually pass many of the algebraic structures over here to this setting, but you have to stop talking about algebraic varieties and start talking about algebraic foliations. OK? So the idea is the following. So take F to be, excuse me, an algebraic family. I'm going to be imprecise now on purpose, instead of by accident, of varieties, of algebraic varieties in omega. So you can think of some Hilbert scheme if you want, or you can take some much more restricted family, any sort of algebraic family. And I'll give some concrete examples, well, some, in a minute. And now we're going to assume that F is GC invariant as a family, not each algebraic variety individually. So in particular, one easy way to build this is take your favorite algebraic variety and just look at its GC translates. That's an algebraic action, so that'll be an algebraic family, and everybody's sort of happy. So these things are very common. It's not some esoteric thing we're talking about. OK, so then if we look at pi of f, so we push forward the entire family at once, no individual guy is algebraic, but the whole thing becomes an algebraic foliation. So this is an, and I'm using this word, if you know a technical meaning of this word, I'm not yet using it. But I don't know how else to describe it, because I can't find anything in literature. So let me just call it an algebraic foliation on X. So said informally, and I'll say it a little more formally in a second, you can write down sufficiently complicated differential equations such that on X, such that their solutions are exactly locally the images of these f guys. OK? So let me, oh yeah, I have time, I think. So let me go a little bit towards making this precise. So what sort of, and I ask this partly because I want to know the answer, but what's sort of the right way to capture sort of complicated algebraic foliations, sort of differential equations on a space? I'm not sure. But the most flexible one seems to be the notion of jet spaces. And this is the language in which we do most of our work. So let me just define these briefly for those who haven't seen them before. So I'll say a few different things. So first of all, let me make sure I get the notation right, because it could get a little tricky. Yeah. So I'm sorry? It will be a foliation once enough things happen. But if there's a more general notion, then I'd be very curious in the right way to formulate it. Yeah, somehow much of what we do here, I'm sure, is in the literature in other language that we're just not competent to read. So, but this is the way that we're setting it up. So define this analytic or algebraic scheme. I'm going to write it to be spec of you take C adjoint D variables and you mod out by the maximal ideal to the power m plus 1. Okay, so this is sort of a single point, but with infinitesimal structure up to order m, is how you think about it. And then we can define a jet space for any analytic space X to just be maps from this guy into X. So in other words, you can think about it as germs of maps from C to the D to X up to order m. Okay, it's concretely what it is. And if you start with analytic variety, you get some analytic variety out of it. If you start with an algebraic variety, you can get an algebraic structure out of it. It's very factorial and all of that great stuff. So it's got tons of properties. And so some sort of simple cases are if you take J0 dx, you just get x back. It's maps from a point. If you look at J11x, you get the tangent bundle of x. So it's just a much more general infinitesimal structure than that. OK, so said precisely now, given our family F over there that we're starting with, we can get an actual algebraic subvariety which I'll call V sub F inside, well, inside, let me write it as inside here, where you want D, so where D is the dimension of the varieties in F. And m is just a big number. In particular, you want m to be big enough such that the infinitesimal structure to order m at a point determines which guy you are in F. And it's not hard to show you can do that. Just some no-theoreticity argument. And what is the subvariety? Well, it's literally those germs to order m which land in something contained in F. So this is an honest-to-God algebraic thing. Moreover, VF is GC invariant. There's a natural action, because everything is so functorial, there's a natural action of the group also on the tangent space. And because our F was assumed to be G invariant, it follows pretty easily VF is GC invariant. And so we get a closed analytic subvariety which I'll call VF tilde, let's say, inside the corresponding jet space of X, just by quotienting out by GC. And the quotient of the jet space of something by a group is the jet space of the quotient, assuming the group is sufficiently freely acting. Oh, sorry. OK. All right, so now theorem. This is algebraic. So note, by the way, that we're not in any like counterfactual world or anything like that. This really is a sort of an interesting algebraic subvariety of the jet space of a Shimura variety, to which you can sort of ask questions, and we prove some theorems about it and stuff. So we didn't have to assume anything about things being too large dimension. This is sort of really a thing you can talk about. And I don't have time to do an example, unfortunately, but an easy example to work out, which I'll say in words, is if you look at the exponential map essentially what's happening is if you take a power series to order m, and you take it log 1 plus that power series, then that becomes actually an algebraic transformation, assuming you cut it off to order m, which you can just see. I mean, eventually the Taylor series just stops, you get a finite sum and such. And that's basically what's happening over here, but in a much more complicated setup with Shimura varieties, and it becomes sort of hard to write things down explicitly. So let me say just a word or two about the proof of this. So in the projective case, this is Chow's lemma, or Chow's theorem? I don't know. Chow's theorem. Just saying that algebraic analytic subvarieties that are closed of projective subvarieties, objective varieties are algebraic. In the affine case, the way that Gaming did it before is he sort of made appropriate growth metrics and differential forms and did some differential geometry to make it algebraic. But in fact, the language of definability sort of gives you a catch-all way to prove theorems like this. So in the general case, it follows from a wonderful theorem of Pirzul and Starchenko called definable Chow, which just says that you can forget about projective. You can take analytic subvarieties of just quasi-projective algebraic varieties, and those will for free be algebraic, assuming you're definable in some O-minimal structure. And this ends up simplifying sort of a myriad of algebraicity proofs that exist in the literature, which again, I'll talk about some in my next lecture. OK, so then what's the punchline? Let me get to the punchline of this whole setup, because OK, we have this great algebraic subvariety, it descends downstairs, we're talking about jet spaces, but what's the point? So the upshot is, let's look at the following set. Let's look at the set of points in our variety W.
What are you now explaining? Case 2 or what?
I'm explaining what to do in general for the Ax-Schanuel case, just the general mock idea. But yeah, let's go back to this sort of setup. And his general idea is, suppose you have a variety W downstairs, and look at a general point P such that there exists a variety V in omega in some family F. And you can take F to be translates of a given guy, or you can just take F to be a Hilbert scheme. It doesn't really matter. Just don't make F too big so that it's still algebraic, such that the dimension of the inverse image of W with V at P is at least some number K. So look at the points at W where you can get a counterexample to Ax-Schanuel upstairs. Then this set is algebraic for any K and for any W. Why? Because now, instead of having to go upstairs and talk about algebraic guides V up there, which are transcendental, so that's sort of a bad thing to do, what we can do now is say, well, look, we have this sort of complicated differential equation downstairs, and all we're asking for are those points W, where if you solve that equation, then you're going to get locally, you'll get some intersection, which is at least this big. Everything I've said is definable in finite order, and so everything's algebraic, and so this for free is some algebraic constructible set. So what this does is it goes back to the original idea I said, where we start with one pair VW, which gives you a counterexample, and allows you to make many more. Because before we had a single VW, and we used monodromy to move V around. But now we don't have to do that. We can just stay on W, and we can say, well, OK, suppose somewhere you get this bad intersection. Then for free, by this algebraicity property, you can move to other points and get better intersections as well. So it gives you a much more robust way to sort of grow this W. So I don't have time, and I wasn't going to anyways, to complete the proof. But the idea is, once you have this, it sort of combines very nicely with this framework, because you can say a lot more about the set I and stuff like that. And it essentially allows you to reduce to the case where the stabilizer is normal, and then you can take quotients, and everything sort of works out. All right. Yeah, let me just stop here. Thank you very much.